Hey, Sweet Pea. So something's poisonous if you putting it in your mouth will harm you, and it's venomous if it putting you in its mouth will harm you. Not exactly, but most animals do use their teeth or mandibles to get the venom into your bloodstream. All venomous really means is that it needs to get some sort of toxin into your bloodstream to actually do harm to you. Like, you could drink cobra venom and you'd be fine. I mean, don't actually do that. If you have a cut in your mouth or an ulcer in your stomach, it will do harm to you, but it needs to get into your bloodstream to actually harm you, right? That's the difference between venom and poison. Tarantulas are covered in something called urticating hairs, which are these little hairs that have toxins on them. And when tarantulas are threatened, they'll like shake off a bunch of the hairs, they'll float into the wind, get in your eyes and skin and mucous membranes and just cause a lot of irritation. And that's considered venomous because it needs to get into your, like bloodstream to have an effect. Right? But the thing about that is if toxic hairs are considered venomous, then plants should be venomous a lot of the time. Like stinging nettles in the gimpy gimpy plant should be considered venomous because the way that they deliver toxins to the things that they're delivering toxins to is through venomous hairs, or poisonous hairs, I suppose. I don't know. Another question I've always had is if you are heating your house, does turning off lights or turning off electronics actually do anything? Because waste always goes to heat eventually, right? Like waste power always eventually ends up as heat, I don't know. So if you have like an electric space heater plugged in next to your PC, does turning your PC off actually save power when all of the energy that was going into the PC eventually ended up as heat? Or does it just make the space heater run more and therefore the ultimate energy costs are the same? Presuming you didn't like change the temperature of the room, right? Like, does that make sense? Hey, Sweet Pea, so when it comes to infectious diseases, you have viral infections, you have bacterial infections, and you have something called a prion disease. And a prion is a protein that's folded in just the right incorrect way so that when it encounters other proteins of the same type that are folded more correctly for our purposes, it unfolds them and folds them incorrectly, right? So you have mad cow disease, you have Creutzfeldt-Jakob syndrome, and when a human gets mad cow disease, it's called variant Creutzfeldt-Jakob syndrome. The scary thing about prions is that they need to be heated to like 900 degrees Fahrenheit for an extended period of time, or much hotter than that, to break down the prion. They can't just be cooked at like normal temperatures like other viruses or bacterial infections can, right? They don't get denatured at low temperatures. You need to entirely destroy them to prevent the infection. And one of the weirdest prion diseases is something called fatal familial insomnia, which is this progressive degenerative disorder in which you stop being able to sleep, and because you can't sleep, your mind slowly deteriorates until you eventually pass away, which is quite strange. I love you. Also, that's probably what King Tut had, maybe. We don't know. Hey, Sweet Pea. So blue eyes are blue not because they contain a blue pigment, but because they're structurally blue, meaning the gaps in the iris preferentially reflect blue light and give them a blue tinge. Green eyes are green because they contain a yellow pigment, which combines with the blue light reflected by the iris and makes us perceive them as green. Brown eyes are brown because they contain a brown pigment called melanin, and hazel eyes happen when you have both a yellow pigment and a brown pigment. You can have different kinds of heterochromia, which is when different parts of your eyes are different colors. You can have central heterochromia, which is when the middle part of both eyes is a different color than the outer part of both eyes. You can have sectoral heterochromia, which is when one part of one eye, like one sector of one eye, is a different color than the rest of both eyes, right? And you can have complete heterochromia, which is when one eye is a complete different color than the other eye, right? You can also have gray eyes, which happen when you have blue eyes with just enough melanin to dim the blue light, but not make it brown. So it just looks like a pale gray, slightly blue color. And in the right lighting, it can look slightly purple, like with Elizabeth Taylor. But purple eyes don't actually exist, as far as I know. I love you. Hey, Sweet Pea. So in the 1970s, Ford produced this car called the Pinto. It was rushed through development and almost every part of the car had issues. It was a very crappy car, but the worst of those issues was that the gas tank wasn't properly protected from rear-end collisions, which are pretty common. So if the Pinto was rear-ended in a pretty low-speed collision, it could cause the gas tank to just violently explode. And a lot of people were killed by Pintos exploding, right? Now, Teslas have a battery that's on the underside, and if it's punctured in a low-speed collision, it can cause the entire car to violently explode, and it is very difficult to put the fire out after it has started burning. In fact, Pintos were only ever shown to kill about 20 people, slightly more than 20 people, But Teslas have killed way more than that. And that's only through the explosions. There's also autopilot deaths because Teslas were rushed through development, and Elon Musk is a narcissist who insists on believing that everything he does is perfect, no matter how flawed it actually is. I don't know why Teslas have this magnificent reputation when they're basically just very shiny Pintos. They're gonna explode and kill you. You shouldn't trust them. I love you.
Hey, Sweet Pea. So temperature is a measure of the average speed of the particles inside of an object. It's kind of unrelated to the kinetic energy inside of an object. So you could have two different objects at the same temperature with dramatically different thermal energies because one has a much larger particle size and much stronger intermolecular bonds, right? And the one with less thermal energy has much smaller particle sizes and much weaker intermolecular bonds. Water, for instance, has a very high specific heat capacity. Specific heat capacity is what it's called when you're talking about the amount of energy it takes to raise the temperature of an object. And water specific heat capacity comes from its ability to form incredibly strong intermolecular forces called van der Waals forces. And it can form those forces because it has a hydrogen bonded to an incredibly electronegative element, which makes it a very, very polar molecule. And you have an imbalance of electrons on either side of a water molecule, meaning that it can actually transfer charges between water molecules and form these matrices of unbalanced charges that are very, very strong. And it takes a lot of energy to make water increase in temperature because of that, because they do not want to separate from other water molecules. It's also why water has an incredibly high surface tension and why water increases in volume when it freezes, unlike every other liquid. I love you. That's not entirely true. Other liquids with very strong intermolecular forces can also increase in volume when they freeze. But water is unique.
Hey, Sweet Pea, so a lot of things had to line up just right on Earth for life as we know it to happen. Like, if we didn't have a molten core, we wouldn't have a magnetic field. And then we wouldn't be able to redirect charged particles coming from the sun that might remove our atmosphere if we lacked a magnetic field. That's the most likely hypothesis for why Mars has much less of an atmosphere than we do, because they don't have a magnetic field because they lack a molten core, right? And we only have a molten core because we have a sufficient amount of radioactive isotopes in our planet, in the core of our planet, breaking down and heating up the core of our planet and keeping it molten, right? Like, there's not enough energy coming from the sun to keep the core of our planet molten, and our planet doesn't trap energy in a way that would allow the core of our planet to stay molten like that, right? There's radioactive isotopes breaking down and maintaining the molten state of the core of our planet. So if those isotopes weren't present in a sufficient level, we wouldn't have a molten core and therefore wouldn't have a magnetic field and wouldn't have an atmosphere and wouldn't have life as we know it. And while tidal forces might not be necessary for life as we know it now, if you consider how important tidal ecosystems were to the development of early life, we definitely needed a moon of a sufficiently large size to develop life as we know it, right? And who knows how common that is in the galaxy and the universe, right? It could be incredibly uncommon. And we have to have a tilt to have seasons, and if we didn't have seasons, we definitely wouldn't have life as we know it. But the thing is like, even though all of these factors together are incredibly uncommon, right? Like, any one of these factors might be reasonably uncommon or even common, but all of them together is very uncommon. The fact that Earth has all of these factors doesn't make Earth designed by some divine entity, right? Because if you were to imagine an infinite universe in which it was impossible, nearly impossible rather, like as close to as impossible as it can be without being impossible for life to develop, but there was at least one place where life could develop, right? Just by random chance. Life would develop in the place where that was possible, and therefore it would observe its environment, and it would go, wow, this environment is capable of sustaining me. And like, obviously, the environment life is in is capable of sustaining the life that is in it. That must be true, right?
Hello, my love. So nicotine is an acetylcholine agonist, meaning it bonds to and activates nicotinic acetylcholine receptors, which are one of two different kinds of acetylcholine receptors in our bodies, right? And that makes us have a bunch of different fun effects, including cancer, although it's actually not the activation of the acetylcholine receptors that cause the cancer. That causes the heart disease. Nicotine, by other means, causes the mutagenic effects that lead to cancer eventually, right? And tobacco plants produce nicotine not because they want to attract us or because they want to kill us, but because they're actually trying to kill insects. It's a neurotoxic insecticide, right? And when we're exposed to nicotine repeatedly, we get an upregulation of our nicotinic acetylcholine receptors, meaning we can perceive more nicotine more strongly when we are exposed to it repeatedly, which makes it incredibly addictive and very hard to quit. Most drugs have a downregulation effect, which actually makes them also very addictive through a different method. But, nevertheless, nicotine is incredibly hard to quit. I love you.
Hey, Sweet Pea. So alcohol is a positive allosteric modulator as well as an agonist of the GABA A receptor, meaning it bonds to the GABA A receptor and makes GABA activate it more strongly, as well as activating it on its own without any GABA present, right? And GABA is this neurotransmitter that regulates the strength of the electrical signals passing through the neurons in your brain. It makes the electrical signals less strong. And if your body gets used to an excess of alcohol or an excess of GABA, it can decrease the sensitivity of those GABA receptors and also increase the sensitivity and presence of NMDA receptors, which kind of do the opposite of GABA. They excite your neurons. And then when you quit alcohol, those excitatory receptors can pump an excess of calcium ions into your neurons and even cause cell death if it's severe enough, but definitely cause a bunch of severe side effects that we call withdrawal, which is why binge drinking is very, very bad, because you repeatedly go through those withdrawal side effects, right? And you don't want to do that. You don't want to change your neurochemistry in such a way that you're more prone to anxiety just because you want to have fun sometimes. And if you can't handle moderation, I would highly recommend that you just quit it entirely. I know I can't handle moderation because if I have a little bit, I need to have a lot more than that. And some people are like that. It's a genetic thing, even. It's called alcoholism. And I love you, even if you have it. You're not broken. You're just sick. And that's okay. It just means you can't drink. That's it. Hey, Sweet Pea. So from a technical perspective, there's a big difference between a deflagration and a detonation. Something like gasoline or black powder deflagrates, meaning that it doesn't actually break the sound barrier, and unless confined, it won't create a shock wave, right? Whereas a high explosive, like ammonium nitrate mixed with diesel or nitroglycerin, will detonate even unconfined and create a shock wave because it produces gases faster than the gases can leave the surrounding area, right? Faster than the speed of sound, because that's how quickly gases can move. And as the gases build up pressure, it forms a shock wave that moves at the speed of sound out. And that's the bang you hear. And it also can blow you backwards if it's strong enough and big enough, right? Gasoline confined can become an explosive, and so can black powder. That's what a low explosive is, and that's the difference between a low explosive and a high explosive. Is a low explosive needs to be confined, like contained in some sort of, bullet casing or something, in order to actually detonate, right? Otherwise it just deflagrates. I love you.